Hey everybody, I'd love to introduce Miguel Heleno from the Berkeley lab, who has been focusing on modeling and planning power grids. Welcome, Miguel.
Hi, thank you very much for the opportunity to present and share a little bit about power distribution grid planning. My name is Miguel Heleno. I'm a staff scientist at Lawrence Berkeley National Laboratory. I don't know, I guess you've had people from other national laboratories presenting. The Lawrence Berkeley National Lab is part of the UC, University of California, Berkeley, and we are owned by the Department of Energy. So our infrastructure is and funding is federal, and we are managed by the University of California. So we do a lot of research to the federal government, also to the California Energy Department's Public Utility Commission, and of course a lot of partnerships with the private sector as well. My team focuses more on optimization applied to the power grid. And here I'm going to talk just about one fraction of that work, which is related to the distribution grid planning. So feel free to ask questions if they are quick in between throughout the presentation. I will have organize this to have some moments of where we can have a little of a break to ask questions. And yeah, so feel free to interrupt if there is something quick. If not, wait for the break moment. So what is actual power distribution grid planning? And to answer that question, I'm gonna give just an overview about power distribution grids. So as you see in this diagram here on the top left, you see that electricity grid, as you may know, is generated typically in big power plants. Then it gets transferred for long distances in what we call the transmission system, and then it goes, gets hooked into a substation or some sort of like neighborhood type of a large transformer, and then gets distributed to our neighborhoods and cities or towns through distribution power lines. This type of structure, it is very present in our lives, and is also the main driver of our distribution of our bills. So when we look at the distribution infrastructure costs, so there's more like small, cheap investments, cheap type of infrastructure in the distribution grid. They account for 32% of the overall U.S. Investor-owned utilities investment. So it is around 2025 is around 32% of the capital investments of the national investor-owned utilities is on distribution grid costs. Why? Because although these are very small, relatively small equipment and relatively cheap and established technologies, they are a lot. There's a lot of them, right? Like, for when you build like a big power line, it's very expensive. One of those big transmission power lines that you see in the highway when you drive, those are very expensive infrastructure, but there's relatively few of them in a country in comparison to like the amount of distribution infrastructure we have. And there is also very little, because there's a lot of infrastructure, utilities keep not don't keep a very good track of this infrastructure. There is not a lot of emphasis in planning this infrastructure because each specific investment is relatively cheap. But when you look at the whole problem, it's a very big problem. And as you know, the grid is also transforming. So there is a lot of new things that we need to connect to this edge type of network. And this is, things related to solar photovoltaic, electric vehicles, all kinds of battery storage, some controls, some different types of demands, like the electrification of, for example, heating and cooling equipments. There is more HVAC systems. So there has been really like a lot of need for more and more of this distribution grid infrastructure. And the chart here on the right shows you, this is a study by the California Public Utility Commission on understanding what's the electrification impacts on this distribution infrastructure. And this is just related to electric vehicles. And basically what they predict is by 2035, there is a $50 billion of additional investments needed to integrate all this infrastructure. And this is just California. So this is a very important problem, I think, in the power sector, and there has been growing attention to this problem. Now, let's understand what is this problem from a conceptual point of view, and then a little bit from the mathematical point of view. So when we're talking about distribution grid planning, we are talking about basically making investments in the power infrastructure of the network, and those investments can be, this new power lines, sort of like, by reinforcing new power lines or adding new ties here, like, you want to interconnect the circuits. So here you can see is like, the nodes of this network are consumers, and say the branches are power lines or transformers, and there is going to be like different substations, different like connections to the transmission that need to be upgraded throughout the time. There's a need to build redundancy around this. There's need to place some sort of like which we call voltage control and automation in the nodes. There is also now the interconnection of distributed resources. Those can be batteries, distributed generation, typically owned and controlled by the utility. So these are not your solar systems or your battery systems at home, but these are often like, things connected at the lower level of the grid that are connected by the distribution utility. So though this is sort of like this type of planning problem is trying to understand what is the optimal or sort of like the least cost combination of these resources that will make the grid feasible and safe to operate and reliable from the perspective of the service of power. How does this mean mathematically? So mathematically, this is a mixed integer nonlinear problem, where of course your investments are integer because they represent different options, portfolio options of investment in each of these technologies. And it's nonlinear mainly because of the way the grid power flow works. I for those who have heard about it, these are a generic representation of the power flow equations. And these power flow equations are based on, nodal power balance. This is like basically making sure that voltages and power is constant across nodes, and is captured also like the impact of energy flows into the voltage of the distribution grid. Those voltages and this power have, of course, technical limits that you have to respect, And then power flows in between nodes through lines, and this is called the branch flow, which depends on the voltage and the power. And basically, because the power depends on the voltage and the voltage depends on the power, this is a very high nonlinear problem. This is just problem to express the operation of the system. But when you go and put this in a optimization problem that tries to basically minimize the cost of these integer investments, and we have to guarantee that this nonlinear constraints are satisfied in every single time for every kind of possible future scenario that can realize. We are really talking about a very high dimensional problem. And there is the aspect of this, it's important to note that this power flow equations or optimal power flow equations are hard feasibility constraints. So things that or solutions that lead to a close enough or close to the feasible range but are unfeasible are not admissible, because the grid has always to maintain its technical limits. And it's high dimensional mainly for two reasons. One, there's two main dimensions here. One is the nodes, the number of nodes, and those are in the range of thousands in the real distribution grid. We're talking about the temporal resolution. These are typically like how 15 minutes to hour resolution over a year, or multiple years. Normally there is a year used, and then there is different scenarios in which there is a demand, different scenarios of demand, different things that can occur. So this is where things can actually explode. So in a nutshell, this is a mixed integer nonlinear problem where the problem is not much, the combinatorial aspect of the investments of the solution space here in terms of investments, but it's more about how this is more about the operations and the different combinations of scenarios that can lead to understanding the best decisions. And I'm at the end of my first introductory part. So if there's any questions, this is the right moment to.
Yeah, one great one is, so notice some of the nonlinearities were due to like sines and cosines and that kind of stuff. Is that because this is specifically AC distribution, and if it was DC, it would be a different, like a notably different planning experience?
Yes. So I think that is DC, that is two, for those who are not familiar with power systems, I guess the question is about DC. There is two ways of looking at the question. Like there is DC in the sense of like the power that flows in the lines is actually a DC power, and it comes with like Tesla versus Edison, AC versus DC currents. That's not how the power operates. So our distribution grid is mostly AC.
Okay.
Now there is a DC approximation of the AC equations, which basically is a way of linearizing this power flow equations. But what I think this question is relevant for this, or the most relevant aspect of this question has to do with this DC approximation does not work in distribution grids as it works, for example, in transmission grids. And that's because because the distribution grid is very high resistance, because we're talking about smaller conductors. What happens is there is a high impact on the voltage. So basically you cannot linearize the relationship between voltage and power. as you do in the DC. So in the DC, the power flow, you can say, okay, my voltage are always going to be around the same values, so I can, assume a linear relationship between, say, power and currents. Here, you cannot do the same because there is actually this is very non-linear. So yeah.
And then one more, so you said it's hourly resolution, but a bunch of phenomena that are relevant would be solar changes by the second, the wind, same thing, even demand changes rapidly. So is hourly adequate, or is it just a computational limit, or how should we think about it?
That's a good question. So there is another dimension of planning. So here we are talking about the economic planning. So here, what matters is really to understand what are the optimal combination of investments. Then when this planning solution, say, I know exactly what are my distributed generation, how my grid is going to be connected. So following this planning stage, there is another planning stage that has to do on how, these things behave in a more dynamic form. And this is where you look at like second and sub-second behaviors of the grid to sort of like, help set up some of the protections, help set up some of the controls of the grid. And this is sort of like another stage of planning that I'm not covering here. But yes, but say here is we just look at this steady state form of the grid and our resolution to sort of understand what are like the big portfolio of decisions that we have to make.
Got it. Yeah, thank you very much.
So I'm going to focus. So I've been working on this for like the last 10 years. So I have a lot to share. So when I was preparing this talk, I decided to, I'm going to focus on the most recent things we have done that we believe are like, potentially of value here. And I'm going to focus the next part of this talk talking about the scenarios and the uncertainty because we have these hard feasibility constraints, and because these constraints have to be strictly enforced in all times, in all across all scenarios. And I'm going to give you an example where these scenarios can be really explosive, and we have to find a way of reducing these scenarios. So my first part is going to be about reducing the uncertainty space when we're talking about solar adoption. We're talking about the distribution grid, and I'm going to give the case of solar adoption. And really the problem we're trying to do, so we're having the same issue, which is like we're trying to plan our distribution grid. So trying to understand what is the best size for this corridor. We're trying to understand what are other options for, like, for example, placing utility, distributed generation, or storage. And we have this problem where, like, consumers can adopt solar or solar PV, and this is represented here by these yellow dots. And this residential solar, could also be it could also be, this could also be demand. It's the same problem. But the issue is the solar can happen anytime in between planning cycles. So the distribution grid utilities typically plan their investments in sort of like 5 to 10 year horizons, right? So when you make a decision now about what's your best, equipment to put in the grid, this thing will gonna stay there for the next 10 years. So that is like sort of like an uncertainty space of like in those 10 years, a lot of things can happen in terms of adoption. So when we look at this at an aggregated scale, here are different trajectories of adoption. So if we look at the aggregated solar PV capacity in the grid throughout these 10 years of planning horizons, you can see, a lot of these things can evolve on an aggregated scale. And typically what utilities do is they take this average scenario as their what they would plan for, and then they want to be robust to these maximum and minimum scenarios. What we try to say is like this doesn't work necessarily, because that is, the total adoption. If you look at what happens in the distribution grid, if you take the extreme scenarios equal to the aggregated scenarios, so there are this, you have, this is an hour of the day with different solar penetration. So of course, when there is daylight here around hour 12, you will see that is a lot of, your load, your demand drops significantly, and this can cause a problem to the grid in some extreme scenarios as well. And these are all aggregated forms of looking at the grid. There's another aspect that is the more important, is like where actually inside the grid this solar will happen. So what are the different combinations of adoption of solar technologies that can stress the grid in very particular and localized areas that would require very specific investments. So this is something that utilities don't look at nowadays, because there is no way to solve this problem. There is no way to sort of like, there is billions, hundreds of millions, I don't know what's depending on the nodes of the grid, the number of consumers, the combination of possible scenarios of adoption is very large, and utilities should, there is no way to prepare for all these scenarios. So the problem we try to solve here is like, what are the few scenarios that the utilities should look at to really plan the system and solve this optimization problem in a tractable form. So we address this through Bayesian optimization, where really what we're really trying to identify is these most critical scenarios that are required for planning the grid, and trying to find these critical scenarios in the high dimensional space with some statistical guarantees. And so the critical scenarios for us and for the grid here, we're trying to identify the scenarios that would cause problems that are unique, problems that are not encapsulated in other scenarios. So because we want to capture what's the most diversity of problems that can happen into the grid, because with there we're going to have also the most the total set of solutions that would guarantee our feasibility. So this is mainly what we're trying to do. So we take a grid and divide it into some groups of this is for nodal feasibilities. And then we take the power flow and the flow feasibilities, and we write these stress functions that are based on what are the worst case voltage problems and power flow problems. And so for each scenario of adoption, we measure stress based on this function, and we construct a Gaussian process for each of these functions. And then we create a surrogate model to sort of estimate the stress of each of these functions going forward. And we as we sample different scenarios of adoption, and then we guide this Bayesian optimization process through this acquisition function that basically calculates the probability that a scenario, the next scenario is non-dominated. So if you look at the figure here, what we do is, if you take two objectives, and these objectives are like two levels of stress instead of like, one scenario of adoption would cause, different stresses in the grid. And this is sort of like, say, F3 can be voltage in one node, F8 can be, a power flow in a given line. And, we take this for each sample, we calculate this this stress function across all dimensions, and then we build the Bayesian optimization model that sort of like progresses through these functions and captures this sort of like what are the ones that are non-dominated across all these objections. So we are not trying to find the scenarios that are more likely. We're not trying to find the scenarios that are more stressful from the grid. We were trying to find the scenarios that bring unique patterns of stress. And we as we go and see, we can calculate the probability that the next scenario is non-dominated scenario. And then with that, we can also have a stopping criteria for sort of a statistical guarantee that it's sort of like that is a highly a likelihood that we found the set of scenarios that are non-dominated. So this is all described in this IEEE Transactions and Power System paper that was published early this year. When you look at the results, like here we compare this against to sort of like naive and greedy algorithms, and like sort of like more of based on full search space and random against actually like a Bayesian optimization model. And I do like then I do a brute force search over a high number of scenarios to sort of like validate this. And we found that this identifies the most critical scenarios in this high dimensional space very fast, because we are progressing towards like finding what are the scenarios that are more dominated, and sort of like discard the ones that we have seen before or have seen similar behaviors and stresses before. So we found this is relatively fast. This is in the paper here. There is like a test in 2 feeders. These feeders are not necessarily very big in terms of number of buses, but we tested this against a high number. This is a high number of simulated scenarios for the purpose of the brute force and checking our cases. And we realized that, so we were able to compare more or less how the critical scenarios compare with the real scenarios. So here we see that there are 15 scenarios that are unique in relative to buses violations, and 32 for line violations, and we found like 13 of them and 31. So here you can see like although here we tested 9,200 scenarios, there's only 15 and 32, so 47 scenarios that are actually relevant from a utility planning perspective. And we found most of them, and the same here for a slightly bigger distribution grid, with we find almost all of this scenarios. So this gives us like some confidence in terms of the accuracy of this methodology. So I'll stop here for questions before I go to the next topic.
Yeah, excellent. So for you get the diversity of all scenarios. So I understand how you can get the mins and max, but how confident are you about the realism of these edge scenarios?
Can you ask the question again? Sorry, I didn't understand.
So it seems like you're trying to search for the true, best case and worst case in geographically resolved way, because you're hitting them individuals like substations or nodes, right? But to what extent do we know whether you're not assigning real probabilities to these events? As far as I can tell, it seems like you're really trying to get the outer envelope of the space. So how do you know about the probability, realism, that kind of stuff?
That is, we assume that we assume that every consumer can adopt with the same probability in this case, right? That is the probability of a solar popping up and the capacity popping up in the same, and the capacity here is also defined as a function of the load. So we know that, we know the true probability of a scenario to occur, and each scenario is equally likely when we sample. The issue is we're not trying to find what are the most likely scenarios or combination of scenarios to occur. We are trying to find the scenarios that would cause more harm to the grid. And yes, this is because what we're really trying to do is to reduce the number of scenarios we have to look at in the optimization to still guarantee that hard feasibility constraint in the operation. So what we go with, like, we go and guide our patient optimization to find the ones that are really that could lead to grid stresses that we have never seen before in the other scenarios. So
Right.
So the probability has to do, the probability of like sample has to do with like, based on the scenarios that I have and the scenarios that are that I've been finding, how likely it is. So based on what I've been observing as I progress through my Bayesian optimization, what is the likelihood that the next scenario is a non-dominated one, and that probability decreases, of course, over time, right? And that is a threshold that we choose to stop.
So the way of thinking about this is more like penetration testing, where you're trying to destroy the grid and figure out what it's vulnerable to.
Exactly.
Okay. So
yeah, we're trying, but we are not. But we are trying to destroy the grid in the different way that we haven't seen before, right? If I already blew up a certain, say a power flow for a 20%, right? If I see another scenario that blows up that power flow in a flow in a line in the 10%, and I see another scenario that violates a flow in another line by 1%, I will choose that one, because that one, the 1%, I have already a scenario that blew up that power for 20%. So I don't need that one. I'm going to go and find the one that violates some other power by 1%. And of course, it's a combinatorial way. This is not just about one power flow in one line and the other. That's the whole combination of power flows and stresses.
Okay, excellent. Thank you very much.
Yeah. So another thing that I'm going to talk about in terms of scenarios when preparing the scenarios for distribution grids has to do with looking for scenarios that never happened before. Because when we're planning infrastructure, we're planning infrastructure for things that we have seen. But the problem is when we're preparing our infrastructure for things that we have not seen. And I'm going to talk a little bit about it. And there is a case of heat waves. So especially in some areas of the globe, we are seeing more and more heat waves coming, and of course, heat waves drive electric consumption. And normally, what it's currently done in the utility practices is to you predict, you look at your historical weather and load consumption, and with a lot of this more simple methods or more advanced methods like machine learning methods and so on, you can understand or forecast your load in the future based on what you see in the past. And normally these forecasts are used to from the planning perspective to add a sensitivity factor on the peak load to account for potential future weather impacts. That's typically for when you're planning the grid for the next decade. When you plan the grid for the next few months or few days, you look at this weather type of forecast to sort of like inform how there is this thing called rotating power outages. So you will actually have to disconnect some substations during heat waves. So you have to plan for these emergency operations. And when a heat wave comes, you don't have enough power because consumption is very high. So you have to disconnect some consumers, and you have to disconnect them in a rotative way. And there's also the emergency demand response. These are like things like you ask the industry or some large commercial consumers to sort of like reduce their consumption for some time. This to help the grid, right? So the issue with these forecasts and the fact that they are based on extreme on weather, past weather load relationships that are inferred through all kinds of methods, they don't work when you're talking about things we haven't seen in the past. And these are typically, this relationship is very nonlinear. So this is like your demand you are seeing in the grid. This is typically your temperature, like ambient temperature outside. So when it's very cold, your demand is high because people have the electric heating connected, and then there is like when there is like a very nice ambient temperature, as we have here in Northern California and San Francisco. This is like where we are most of the days. We don't need any AC, so your demand is like pretty static relative to temperature. And then when temperature becomes very high, people are start turning their HVAC systems and air conditionings and so on. So really, like, you start having demand going up, and you sort of like project this into the future, trying to like extrapolate, these relationships going forward to sort of forecast demand with temperature. The question is, there's very few observations on the very high temperatures here, and the ones that exist tell us this is a very nonlinear curve here. Here is just a potential one because we really don't know how to describe this. And we don't know how to describe because, there is a moment where a lot of people, when it's very, very hot outside, a lot of people go and like turn their ACs. So the temperature really goes up more than normal. And then there is a moment where it doesn't matter how hot it is. Everybody already has their ACs blowing at the maximum. So temperature can increase, but demand won't, right? So that is this sort of like weird potential trend when things are very, very hot in terms of demand. So how to prepare for that without, of course, without over killing this problem, over investing the grid is also a problem. So what we have done here was, instead of just using data to feed those machine learning methods to forecast loads, we take historical data and grid and calibrate the physics-based model. And this basically, after calibrating this physics-based model, we go and potentially now can forecast any scenario that we haven't seen before. So this is experimental project we have done, where we plugged, information about the building stock. We took the meter infrastructure data, so multiple years of individual consumer data. We took information about thermostat sensors that tell us like how people use their thermostats, and we calibrated this like very detailed urban building model, which is basically for each transformer we see, or each meter of the consumer, and some information about the building there. We create a sort of a twin of this building in a physics-based form that we can now use to simulate anything and assess the impact on the grid. We did that. We took 50,000 consumers in East Portland, Oregon, And we created an individual building twin for each of these consumers. Of course, we use like a bunch of data about their envelope, about their thermostats. Use the ecobee thermostat data. We use the AMI data for 2021 and 2022, actually for 2021 to calibrate, and then 2022 and 2023 to test the model. And of course some weather data. So for in the whole area, we took each building and we created like a twin, and then we simulated and tried to calibrate it the load consumption and peak power to sort of like try to capture through building simulation, trying to infer behavior. And of course, here we are not like using any sort of like machine learning method or anything. This is really just based on physics as of now, because we really want to remove any sort of influence from other models. So what we found here is like we're really relatively well. This can describe heat waves periods based on this. And this is a normal summer. This is a normal winter, which is kind of like weird here. Like the winter, we're not very good because we sort of like calibrated this to be better at replicating summer than winter. So our transition season period is also like not doing very well in terms of the error. And this is all based on manual calibration. So that here you'll see there is these different steps where we're like, there is a paper here that you can go if you are more interested in understanding this. There are like different like manual steps where we're trying to make some assumptions about how people use their cooling, how people use their heating, how people ventilate their homes through natural ventilation, to sort of like infer based on the data what are the actual what is actual behaviors that are leading to this consumption. And our errors here are they sort of like measure the impact of these steps, but really like this is sort of like a preliminary study, and it really like what it suggests is that is like a very good opportunity here to sort of like do this in a closed loop form instead of like a manual process here. There is a way to like employ some sort of like AI based calibration, or do this in a more automatic form, for example, based on patient optimization or something like that, where we can actually like make some parameters about distribution of behaviors across a whole region, distributions of use of natural ventilation, distribution use of cooling and everything, and sort of like try to improve this error metrics. But still, what we captured is the most important part, which is like we capture the true relationship between load and temperature by basically encapsulating this in this physics-based model. And this allow us to really like arrive to a very interesting conclusion. And this is related to sort of like the ability for the consumers to reduce load during extreme heat waves. And so we found that when the temperatures here are very high, this is the ability for consumers to reduce load, and this is like an absolute and percentage. And what we see is like really when the temperature is very high, your ability of consumers to reduce load drops significantly. That's because a lot of the flexible demand is based on thermal, basic cooling equipment, like refrigeration equipment, HVAC equipment that that are okay if they disconnect for a certain amount of time and to help the grid. But of course, when it's very hot, there is no room to disconnect this equipment. So there is this abrupt decrease, and this is typically what utilities rely on for emergency operations. So what we are seeing here is when utilities really need this resource, this resource does not exist. And we went back and looked at California heat wave of 2020, and that is actually the system operator reported that they asked for 800 megawatts of emergency demand response, and only 50%, only 400 megawatts actually responded. So sort of like our there's never been an actual validation of this, and we sort of like arrived to similar numbers here in Portland General Electric. So it was a cool way of like use of this sort of models to capture load during heat waves. And I'm going to start with my final chapter here, but I want to stop here to see if there's questions.
No, it's good. Thank you.
Can I move forward?
Oh, yeah. Yes, please.
Okay. So this is going to be more about the grid itself and how you make decisions under uncertainty in the grid. So there is a topic of grid planning that's called resilience planning, and it has to do with like how to make sure when something really bad happens, utilities can respond to it. They have the infrastructure in place operating to sort of like withstand some of these events. Of course, it's not the case of the picture here during this storm. But the question is, you cannot prepare for everything, right? You cannot prepare for anything that can happen. We really have to put this in a sort of like cost versus risk based. So when you talk about grid resilience, it's important to know that this is really different from what normally called reliability. So when you're planning your infrastructure in the distribution grid, there are things that can go wrong, equipment can fail, and so on. So typically, when equipment fail, and there is an outage, if you say like describe the outage probability as a function of the magnitude of the impact of this outage, you have this very routine events that are somehow frequent, right? That are more frequent, which is like a line blows up or a transformer blows up, and like 2 or 3 consumers are without power. Like there is this neighborhood that is without power, and then this is very common. It's called like routine events. So actually taking care of these events is a reliability problem. And then you have the events that are very, very hard to happen, like major storm, a earthquake, a massive heat wave. And normally these events take a lot of consumers out of the grid. So they are called high impact, low probability events. So they're probably very rare, but they are very impact. And typically in stochastic optimization problems, this probability is so low that it doesn't affect much the results. So what we really have to do is to formulate this problem as a risk mitigation problem, in which when you look at the costs, you look at the cost of the grid in terms of their grid upgrade costs. There is an expected value of those costs, and here is where we account for the routine events, but we have to add another component of this objective function, which is on the costs of the worst case scenarios, the conditional value at risk costs in a stochastic optimization. And of course, you put this into an optimization model, the one I showed, where you have the costs and you have the the nodal balances and so on, right? And the issue here is you have this variable lambda that is a parameter of the optimization that sort of tells you what is the risk aversion of the planner. So if this lambda is 0, it means like you don't care about the optimizing your costs for the worst case scenarios. You just want to talk about what is their average cost. If this lambda is very high, it means like you're putting more emphasis on getting solutions that prevent you from this, that take a look at this like the tail of that distribution of the curve. When you put this in a stochastic optimization, of course, this becomes a very large problem, because there is this amount of scenarios that you're talking about. You are talking about a huge number of scenarios of wrong things that can happen into the grid. And you have this portfolio decisions in the grid. there is this, you have to analyze the investments, and then for each scenario, for each hour, you have to see if the system fails or did not fail. If it failed, what was the duration of that fail? How would you react to that failure? And then, sort of like apply a cut here, operational cut for each of these scenarios of failure that can happen to the grid. And as sort of like composes what is your impact, your loss of load, and how does that impact your cost. So basically, this is how this type of problems are formulated in mathematical optimization. And the issue is this becomes intractable for a very large number of scenarios. So here we use two properties of the system that really are really true in reality, and make us simplify the system, this problem, way much, and solve this in an actual scalable form. So there's two things you consider. One is, and I think this is the most important part. One is that, this is a distribution grid. So most of this grid, when it's not when it's planning, but when it's operating, it's radial. So there are some investments that are irrelevant for the outages. For example, if there is a failure that happens in this part of the grid, any of this equipment fail, there is a bunch of this equipment that can fail. These investments here are irrelevant to solve this, right? There's nothing you can do here to help solve some of this and curtail some of this load. So this allow us to sort of like write what are the sets of investments of outcomes as a function of the investments before we solve the optimization, right? We can say, and because normally you have a relatively small number of investments in comparison to the number of things that can go wrong in the grid. So really, you can describe your loss of load, what can go wrong in the grid, as a function of these investments. And then you can say that, anything that is time coupled can still happen during the operations, during sort of like the central scenario planning. But when something goes wrong, you don't make time coupling operation decisions to prevent things to go wrong. So in other words, if you have a battery in the distribution grid, utilities are not operating this battery thinking that on the probabilities that lines fail and things like that. The battery is going to be doing some sort of market participation or something like that. And then if something fails, yes, the battery can be used to like help and supply things. So with these two assumptions, we can solve, and by describing loss of load as a function of the investments, we can actually decouple this. You still have a time coupling in the main scenario, but all the outage scenarios can be decoupled in time in sort of like the state space. And you sort of like introduce this sort of loss of load cuts into the problem and able to like solve this in a scalable way. There is another transactions and power systems paper that describes this. And this is where we go and like went to Chicago case and the Commonwealth Edison case, and they had proposed they were analyzing three types of investments in the grid. There's like, this is a potential storage placement in the distribution grid, and some of the potential ties here in investment in lines. Here is their historical average failure, the duration, the impact, and you can see that is here. This is like a very high impact, low probability failure, and it was due to a storm in August 2020, like 70 hours without power, some of the consumers. And they were like trying to understand what are, how different risk aversion really plays out here. So we arrived at two solutions. If you go for a risk neutral plan, where you set up the lambda equal to 0, you end up only with a 3-line interconnections that Commonwealth Edison wanted to propose. But if you go to but the worst thing that can happen, your CVAR cost here is going to be $2.6 billion. But if you go for a full risk-averse plan and consider that lambda equal to 1, you not only the 5 lines are selected as optimal solution, but also there is a 1.1 megawatt-hour battery placed in this area here of the grid. So what it really means is your risk aversion here drives your decision, and your system cost here of what happens is the worst case goes to 1.0 million. So by making this risk aversion, you decrease the amount exposure of your system to the catastrophic events. Of course, this depends on how much you value loss of load, and here is a sensitivity analysis around it. Yeah, was rushing a little bit, but I want to make sure there was time for questions.
Excellent. So one thing that's interesting is you're balancing CVAR against a more deterministic cost or expected value cost. But CVAR naturally captures the probability of one of these events. So would that be another way of formulating this? Like if modeling, optimizing for CVAR at 75th percentile, 90th percentile, 99th, and yes, why not go that way?
That's a good question. Because this has to do with this division here. This division here, that is actual there is a level of impact and probability for which utilities are not accountable for. These things of safety and safety, routine failure. So typically a distribution utility is evaluated by the performance in their expected, what's expected in terms of outages, right? So they want to balance how much they invest in the grid and what things can go wrong. So this is why we treat this part as an expectation. This part is treated is typically is regulated in a different way, because it has to do with catastrophic events and help utilities make investments for catastrophe. So it's more for a regulatory perspective that we treat this differently.
Okay, so if you were doing something more holistic, where it's utility and regulators and let's say insurers, so you have all the paying parties, how would the analysis change?
Again, here the idea is if you want to keep the expectation of costs, right? I think keeping the expected value is the same. The question is, you can have different degrees of resilience, right? And that's what we're talking about. They can have the CVAR 95, 70, 85. So it's you can have different degrees to that tail of the distribution. So you can have make this risk averse more granular, and yeah, that'll be possible.
Oh, great. Well, then, yeah, excellent. Thank you very much. This is enlightening.
All right. Thank you very much for the opportunity to present. Yeah. Let me know if there's questions, more questions, reach out to me. There's my emails there. So yeah.